Hello class, Professor Anderson here. Let's take a look at parabolic motion in a little more detail. Okay, what we said a second ago was let's take an object and let's throw it off the top of a building. And if we throw it horizontally off the top of a building, then it follows this parabola and eventually hits the ground. Now let's think about our motion diagrams for a second. Okay? When we talked about motion diagrams, we always drew things like x or y as a function of time. Okay? And if this is y as a function of time, draw that up just a little higher, then I would start up here at height h, and it would go like this. Okay? But we just said that this thing was a parabola. And yet this was y as a function of x. Y on the vertical, x on the horizontal. We said that y versus x gave us a parabola. But now we're mapping something totally different. We're mapping y as a function of time. Is this a parabola? Or is this not a parabola? What do you think? On the right, Stephen.
It is a parabola.
Okay. He says this is also a parabola. Why is this also a parabola?
Because the kinematic equation has t squared in it.
Okay, the kinematic equation has t squared. Let's solve that kinematic equation. Yf equals yi plus vy initial times t plus 1/2 ay t squared. And what we said was, well, let's let h be the height that it starts at, and let's let y final be any position we want, and we'll just call it y. Okay? How does that position y vary as a function of time? Well, y final is now just y. Y initial is h, vy initial is 0, ay is negative g, so I can rewrite that as minus 1/2 gt squared. And now look, I have an equation that looks like this. Stephen, is that the equation of a parabola?
Yes.
Yeah, because it's got a t squared in it, right? Okay. It's inverted, of course, because it has the negative sign. It's offset because we started up here at h, but it is certainly a parabola. But wait a minute, we said this one was a parabola. And this is y versus x. So maybe that was wrong. Maybe this isn't a parabola. What do you guys think? Is this a parabola? Okay. Yeah.
I think both are parabolas.
You think both are parabolas? Because I drew them so carefully that they're both the perfect curve. I think you're right. I think they are both parabolas. But why are they both parabolas? Well, to understand this, let's map out x as a function of time. Okay, what we just mapped was y as a function of time. But if we map x as a function of time, what do we get? I don't know. Let's go back to our kinematic equations. X final equals x initial plus vx initial times t plus 1/2 a sub x t squared. All right, we're going to give you the initial, vxi. And we can also say that xi equals 0 is right where we started from. So x as a function of time now will be 0 plus vxi times t plus, what is a sub x for projectile motion? 0. So that last term is 0. And now look what we get. We get an equation x equals vxi times t. I got my equation for y right there. I have my equation for x right there. And if I map x as a function of time, what does it look like? What is this function?
A line?
A line. Yeah, it's a line. And in fact, the intercept is 0, right? And it's a line that looks like that. That's x as a function of time. What's the slope of the line? Vxi. Okay. How does this help convince us that this is a parabola? Yeah, question.
So is it because they're directly related?
Aha.
Time and maybe distance?
It is because they are directly related. That's exactly right. They are related linearly. If t doubles, x doubles. If t quadruples, x quadruples. They are related in a linear fashion. And so, in fact, we could replace this t over here with x. Okay? And let's do that. We can see really quickly that t is just x divided by vxi. And so, in fact, I could rewrite this whole equation. Y is equal to x minus 1/2 g times x over vxi quantity squared. And now that is the equation of a parabola because y goes like x squared. Okay? The scaling is a little different, of course, but it's exactly the same equation as the one above it. This is definitely a parabola. And now there's kind of something very cool about this last equation. What is really cool about that last equation? What's cool is there's no t in it anymore. There's no time. So if you want to know where that object is going to be, how high it is going to be, at any time, there or there or there, you don't have to know the time. All you have to do is know x. I plug in x, and that tells me exactly how high it's going to be. Okay. This is for a particular case where we launched it horizontally, but we will also derive it for launching it at any other angle. Okay. We will get a similar equation that has y that only depends on x. Questions about this? Okay. Hopefully that is clear. If not, come see me in office hours. Cheers.